In this video, we're going to position the landing gear. We are looking at this starting point where we have the airplane with the wing already installed. So the CG analysis has already been done, and the wing has already been positioned in this phase. So there is a couple of deviations with respect to the exam of 2019. In that exam, we had assumed a position for the engine. In this exercise, you saw I actually drew in the engine, which led to a slightly different position. So we start with an engine which is a little bit more aft than on the exam. It's about 77% of the fuselage length. At least that's where the CG actually resides. And that also gives a little bit different results downstream and also results in a slightly more aft located wing position. We put all the calculations were performed. The sheet has been filled out, and from this sheet I'm starting with the drawing of the most forward and most aft CG location that result from this analysis of the CG excursion. And I do that first of all in the top view. And in the top view, I already drew in on the center line of the airplane. I drew in the mean aerodynamic chord, just for me as to have sort of a visual reference. Now the forward CG is located at 15 meters from the nose, and that is coinciding almost exactly with the most forward, or with the leading edge of the mean aerodynamic chord. And the most aft CG is 70 centimeters behind that at 15.7. So I'm drawing the typical CG symbols in there. And that is my CG excursion. So this is my aft CG, and this is my forward CG. All right, I can copy them also here in the side view. In the side view, for now, I'm assuming that the CG is also located on the center line of the airplane. Right. So the aft CG is the starting point for the positioning of the main landing gear. So we know that when the CG is shifted fully aft, and this airplane is, for example, making a landing, we do not want the center of gravity to touch behind the main landing gear wheel axle, right? Because if that would happen, if the CG would be behind that axle, the airplane, due to inertia, would over-rotate and tip on its nose. Now, I'm deciding here that I choose an angle there, my longitudinal tip over angle, and I'm choosing 12 degrees. So I actually draw a line through the aft CG, 12 degrees. So that is going to be a line that is indicating a boundary or a constraint. So the wheel axle should always be behind that line. So I can indicate also that by these hash marks there. Now the next thing I'm going to do is define the scrape angle of the wing, or of the fuselage, the maximum angle that it can rotate. That can be a little bit lower as the longitudinal tip over angle, but you can also choose it to be the same. I choose it to be the same for now, which means that the fuselage is preventing this airplane to rotate more than 12 degrees. Then it's actually tipping on the ground. And I got to make sure that happens when the oleo is fully compressed, right? So first, let me draw that line. So I'm actually and now I have to draw another line at an angle of 12 degrees. So just to help me out a little bit, I'm making a little bit of a help line that is going to be close to the fuselage, because just doing it by hand positioning your protractor parallel to 12 degrees is a little bit difficult. So I'm constructing this help line that I'm gonna get rid of later on. So you see the help line is not quite touching, but it helps me to align my protractor and actually touch the fuselage somewhere there. Right, so this is my actual constraint, again with some hash marks indicating that the wheel axle needs to be below that line. And now I can also remove the help line that I had drawn in. So I got two lines crossing each other. Now let's take a look at this list of actions that I'm going through here. It says first I need to choose a shock absorber stroke. I didn't actually talk about that yet. It needs to be between 20 and 50 centimeters. Let me choose 40 centimeters for now. Give me a nice stroke. Draw the scrape angle constraint on the wheel with compressed oleo. I already did that. And draw the tip over constraint for axle with extended oleo. So there's a difference between those two constraints. So I got to make sure that my wheel axle is always behind this line in extended position, and it's always below that scrape angle line when it's compressed. So that requires me to do a little bit of searching here, such that I get about 4 millimeters of stroke in between the two. So that's 1, 2, 3, 4. That gives me my axle position exactly here on this point. So it's about 4 millimeters below that scrape angle line, but still behind that longitudinal tip over constraint. Right. So what I'm drawing in is basically the landing gear with the oleo fully extended. Right. Now, prior to this exercise, I'd already determined what the size of the wheels was going to be based on the maximum takeoff weight of this airplane, which is 570 kilonewtons. Based on that, the load classification number of the runway, we estimated the tire pressure, and from that estimated the main wheel diameter. That turned out to be 1 meter, which means I can now draw in the wheel here about that axle point of about 1 meter. So let me get my my wheel template here. Get the 10 millimeter one, and there we have our main wheel for now. Next thing I'm going to do is look at the nose wheel. So the nose wheel needs to be located somewhere in this area, and there's a couple of things that play a role when you decide on the position of the nose wheel. First of all, the nose wheel needs to have sufficient load. If the load on the nose wheel drops below let's say 7-8%, it becomes really hard to steer the airplane because there's not sufficient downforce on that nose wheel. So Roscom suggests here that we need at least 8% of the weight on the nose wheel. And the worst case scenario typically is then when we're looking at the most aft CG position. So in order to compute the length that we need, this Ln variable, we can look at the drawing over here, and we see that Ln is defined as the distance between the center of gravity and the nose wheel, or the nose strut, if you will. Then we have this other variable Lm, that's the distance from the center of gravity to the main landing gear axle. And that is something that we can now actually measure in our drawing, because we have the most aft CG position and we have the axle, and the distance between that is exactly, let me do this correctly, is exactly 90 centimeters. So this Lm, I'm writing it here, Lm equals 0.90. So with this formula and the notion that 8% needs to be on the nose gear, I can now compute what the length from the center of gravity, the aft center of gravity, to the nose wheel is. And with an 8% nose wheel load, that gives me an LN of about 10.4 meters. So let me see where I'm ending up with 10.4 meters. I'm going to end up roughly below the type A door. And now I'm going to make a little bit of a small thought process here, because this wheel is going to go down. It's going to roughly end at the same vertical location as the main landing gear, below the wheel here. So it's the wheel is going to end up somewhere in this location, very close to this location, at least the lower part of the wheel. Why am I doing this exercise? Because I already want to know, if I'm retracting this wheel, where it's going to end up. Why? Because I would like it to end up below my my flight deck. Because below my flight deck I have some space that I'm not using for cargo. Typically I can use that space to store the nose wheel. So I'm measuring this distance here to the lower side of the fuselage, a little bit more inboard, because that's where the hinge point of the nose wheel is going to be, and I'm measuring about 2.5 meters. Then I'm going forward 2.5 meters. And that indeed would put my nose wheel below the flight deck. So that is not a bad location for the nose wheel, right? So I'm iteratively checking where this nose wheel is going to end up. It's below the flight deck, which is good. If it were, for example, a little bit further behind, I would have to do things a little bit differently. I would sacrifice part of my cargo hold for this nose wheel, or I could decide also to make the nose wheel maybe the strut maybe a little bit shorter. But for now, this looks quite good. So I'm gonna draw it in. We have from the Aft CG position 10.4, so that's the right location. And I actually, before, I already estimated that the wheel was going to be 60 centimeters in diameter. Now this airplane, when it's on its nose wheel and its main landing gear, is perfectly level. In practice you often see that the airplanes are dipped down a little bit, so the nose wheel strut can then be a little bit shorter. If you want to take that into account, you can. Typically we do not want the deck angle to fall below 3 degrees, because then it becomes uncomfortable to walk inside the cabin when it's parked, but also for people to load the galleys, for example, with carts. So 3 degrees is really the minimum. I choose to have the airplane nice and level here to make things straightforward and easy. Of course, we cannot leave it like that, because now the wheels are simply hanging. So we need to come up with a strut. So it's a little bit notional here, just making a very thick line, but making sure that the strut ends inside the airplane and having a distinct hinge point inside the airplane. And then I can actually draw with my geometric compass where that wheel is going to end up. You can see that the wheel now nicely ends up below the flight deck. Right, so the next thing we need to do is look at where the wheels need to come in the lateral position. And for that we turn our attention to the front view. First of all, we have this step-by-step process for the undercarriage position for a low swept wing. First thing we need to do is show the axle locations of the nose landing gear and main landing gear, and we can do that both in the top view and in the front view. So let's see what is most convenient to do first. Let's maybe first do the top view, because then I can copy these things in there. directly. So the axle is about, I don't really know where the wheel is going to end up, so I'm making a dashed line for now. So that's where the wheel axle is going to be for the main landing gear. Well, this one's pretty obvious. It's going to be located over there on the center line, obviously. Next thing is the height. So with respect to the center line of the airplane, the wheel is about 3.5 meters below the center line, and both wheels, well, that's the main landing gear wheel axle that I just drew in. Again, I'm using a dashed line here because I don't really know where it's going to be yet. I do know where the nose wheel is going to be. Already computed that we're going to have two nose wheels. So this is where the ground plane is. It's the main gear had a diameter of 1 meter, putting the ground plane 50 centimeters below the main landing gear axle, and then I can draw the nose wheel in very notionally here, leaving some space for the strut. And the dimensions of the wheels come, of course, from the chart where you actually pick the wheels and the tires that you need here. So again, connecting that and adding a strut, which is simply just a thick line. So that's the nose wheel. Lateral position is in the middle. You typically put the nose wheel in the middle unless you have some kind of other reason not to do that, and sometimes there is definitely examples, both civil airplanes and military airplanes, where the wheel is slightly offset, but we put it in the middle for now. Okay, so the first thing we now need to do is determine where this main landing gear wheel needs to be in the lateral position. And we're going to look at two constraints. One is the lateral tip over constraint, so the fact that it doesn't tip over the nose wheel and one main wheel when the airplane is, for example, making a turn. That's one constraint. And the other constraint is the clearance constraint, making sure that the wheel is sufficiently far outboard such that the wing tip is not touching the ground during a banked maneuver. We do not have any engines hanging under the wing because the engine is on the fuselage, which makes it a little bit easier in terms of the lateral positioning. So I'm choosing to have a tip clearance of about 20 centimeters along with a bank angle of 10 degrees. And 10 degrees might sound a lot, but you should think about the off point of this tip when the airplane is both banking and having an increased attitude, for example, during a landing maneuver or during a takeoff maneuver. That point is actually reaching the closest proximity to the ground. So I'm using 10 degrees just to account for both the attitude change and the longitudinal attitude and the banked attitude change. Might seem like a lot, but we will see it's still not going to be sizing for the position of the landing gear. So 20 centimeters below the wingtip, and then an angle of about 10 degrees. And drawing a notional line again, saying, okay, the wheel needs to be below this line. Well, you can see this diagonal line here, the 10-degree line, actually intersects with the main landing gear axle at about 1 meter away from the center line. So even if I would put my wheel 1 meter away from the center line laterally, it would already comply with this bank angle requirement that I impose here. The next requirement we're going to look at that might determine this longitudinal, this lateral position of the main landing gear is the lateral tip over criterion. So the lateral tip over criterion is typically dictated by a certain angle, psi. and that you can find in the slides actually how psi is exactly defined. And with a formula, you can then compute for that lateral tip over angle what the lateral position of the wheels needs to be. And I already did that. I computed that, and it turns out when you compute that the lateral position of the main landing gear strut needs to be at least 3.1 meters away from the symmetry plane there. So that is, as you can see here, that is actually what's going to be sizing the position. So I'm drawing that constraint in here with the hashes indicating that the wheel needs to be to the right of that. Now, next point is at that intersection point between those two lines, so the axle and the constraint line, I'm actually drawing the middle point of the bogey. That's a little bit conservative, but it's okay for now. So the bogey drawing as a square, and then the wheels I draw in as rectangles with the appropriate dimensions taken from the database of tires, right? And then finally I'm drawing in the strut. Well, now that I'm thinking about it, this thing also needs to be stowed, right? So it needs to collapse inside the fuselage if you stow it like this. So I'm wondering, now that I'm drawing it in, if I rotate this thing, can it actually be stowed? So let me take a look at what the length is going to be of the strut when fully extended, and I choose the hinge point inside the wing. It's about 2.3 meters, and I have a wheel that measures 1 meter in diameter, so 50 centimeters in radius. So 2.3 plus 50 centimeters is 2.8 meters, and I have available here 3.1, so that will fit very, very nicely in there. So I'm not too worried about it. Then I can continue drawing my my strut. But if it would have been differently, if it turned out that my strut was too long, such that the wheels would basically interfere when they would retract, you could also choose to put the wings a little bit further outside to allow very easy stowing of the wheels. Right, so now I can also draw in the front view how this stowage process is going to look like. And do the wheels still fit below the floor? Let me check that. The floor is about, let me see, the floor is exactly 1 meter 20, and here 1 meter 20. So indeed the wheels literally touch the floor, so they might have to be a little bit more down, but I think this looks quite believable the way it is. Okay, so we now finished the integration of the wheel in the front view, in the side view, and the last point we need to do is copy that into the top view. So we already had the axle location. Now we can finish that. Right. So now we also need to think about this thing is going to retract inside the fuselage. Maybe it's good for reference to put the spars of the wing in, just to see where that strut would come out with respect to those spars. So the spar location is determined by a choice again. So for example, I'm deciding to put the front spar at 15% of the chord. So 15 times 15% of 5 meters is about 75 centimeters. Same here. So my spar is going to be located over here, and my aft spar, my rear spar I should say, is going to be located, I want to leave at least 25% chord open. So on my root chord, that is 1 meter 25, coinciding with the Aft CG, and on the tip it's 25%, it's 40 centimeters. And then if I just put my protractor here, I can already see that the strut is going to be, if it's going to be straight up, the strut is going to be actually more or less intersecting with that spar, which means the spar position is almost good. I would say I would put the spar a little bit more forward, just to make sure that we can mount the strut behind the aft spar and actually use the inboard part of the aft spar as the bulkhead of the fuel tank. Right, so let me just notionally shift it a little bit aft. It gives me a little bit more space for flaps as well. Now I'm actually, with drawing in those spars, you can see I'm drawing them in all the way to the center airfoil. We know in practice that in the center wing box, the spars are not swept anymore. They're actually going across perpendicular to the longitudinal axis of the fuselage. But notionally, this is quite okay. Now I'm going to retract that those wheels, copying that position of the wheel from the front view here. Dashed line here, marking that, and copying, assuming that it's a perfect perpendicular retraction, copying that here gives me this center point, and I'll draw in the wheels here. And you can see that the wheels will be retracted in that portion. That seems to be quite okay actually. There's plenty of volume inside the fuselage to do that. Wheels are not touching, so we are happy. There's still some clearance, which means that if necessary, the wheel can also grow a little bit. So it seems to be like a good integration. The only problem is that when we are retracting the wheels here, that part of the wing is actually where the flap is located. So in practice, what we will do is we will actually add an auxiliary spar, as we call that, and the auxiliary spar is typically mounted perpendicular to the wing and intersects then the aft spar. So that's an auxiliary spar here between the side of body of the fuselage and the aft spar. And you can see if we put an additional spar there, we are actually interfering a little bit with the wing. So what we will do is we'll add a kink to the wing. So you can see that the integration of the undercarriage requires us to also make modifications to the wing. So that's what I'm going to do next. And I'm keeping things constant from the intersection point onwards of the rear spar and the auxiliary spar. I'm measuring there a distance between trailing edge and rear spar of 1.2 meters. So now I'm going to the side of body. I'm also measuring 1.2 meters there, and I'm simply making a straight line until it connects to the trailing edge. So what I've now done, I've introduced a kink in the trailing edge, and that kink allows you to have behind that auxiliary spar a flap of constant chord. That's going to be your inboard flap. Yeah. So I've added a kink into the wing section, and I will actually erase the original trailing edge that I had. Just to make sure that I convey the message that we actually have a kinked wing rather than a so-called straight tapered wing. So the undercarriage integration, particularly the main gear, has an impact on the wing platform. And that I've shown that over here. If I would do it perfectly right, I should also correct this in the side view. So I'm also marking this spot here, because now my root airfoil is going to grow as well. Assuming the same thickness to chord ratio, my root airfoil is going to look a little bit different. It's going to be a little bit thicker in absolute sense. And that's, from a structural point of view, absolutely not bad at all. That's actually quite desirable. I'm going to put in the kink also in just a little bit, but let me first draw the new root profile in. There it is. And the next thing I need to do is copy the kink position, which is not going to be very difficult, because it's going to be, it's just of course the same position as the trailing edge of the airfoil. So chopping that trailing edge line there and making it that go up perfectly straight, so we can actually see the kink also in the side view. Right, so modified the root airfoil, modified the platform shape, added a trailing edge kink, all to make sure that this undercarriage can actually be retracted. Now, we added a little bit of a triangle here, which means that the surface area of the wing has actually grown. Now, if you perform this as part of your airplane design process, and you started with a certain wing area based on your wing loading and power loading or thrust to weight ratio diagram, then you are now artificially adding additional wing area, meaning that your wing loading actually decreases. So that means that you are going to be a little bit more conservative than what you have estimated in your wing loading diagram, and that's something to keep in mind, or maybe take into account in the next iteration, because now you can actually compute how much additional wing area you've actually added by adding this triangle, which we typically call a Yehudi. All right, so that finalizes the integration of the landing gear. We have the landing gear in top view, front view, and in side view, all consistent with the modification to the wing as well. So thank you for watching. I hope this was very helpful.